a quick recap. TK, remember we were doing the colored complex thing that's still not over yet. So we had to figure out why our transition metals colored. So it had something to do with the d-subshell, where you had five d orbitals, and this is how they looked. TK, one of them had a different shape. The other ones, the typical ones. The electron density was existing on different planes. TK, between the xy plane, the xz plane, yz plane between the y and z axis. X square minus y square is when the electron density is lying on the x and y axis. Each orbital can have 2 electrons maximum. And then there was dz square. And I told you that three of these orbitals, three of them, their electron density was lying between the axes, while two of them, this one and this one, the electron density was lying on the axis. Either it's lying on the x and y axis. Over here, the electron density, the electron is buzzing on the z axis. So you had to keep that in mind. And so that was what your d-subshell was. And then I talked about the fact that the d-subshell was degenerate, which means that they were identical. They had exactly the same energy level, just like px, py, pz. The only difference is the orientation. So they all were equivalent. All of them were exactly the same. All these d-subshell were exactly the same. They were equivalent. The only difference is that they were oriented in a different way. The last one had a different shape, but otherwise they even looked exactly the same as well. I said so, but what happens is, this is what we did last time. What happened was that when a copper ion, and this is the d-subshell, so let's assume this is the copper plus 2 ion, and the d-subshell is inside it. There would be areas where the electron density of the d orbital would be between the axis, and there's some d orbitals where the electron density is lying on the axis. So the d-subshell is split into two sets. So let me just circle this. So imagine this is your copper ion, and the copper ion is +2, and it attracts all these ligands. Now, in an octahedral complex where 6 ligands get attached to the copper ion, all the lone pairs they approach on the axis. So there's a lone pair on the N which is getting attracted to the copper ion. There's a lone pair on N which is getting attracted to the copper ion. So all these lone pairs, the negative charge on those lone pairs, they're all coming on the axis. And nothing is happening. There's just a dative bond getting formed. Ammonia is not doing anything. Ammonia is just sticking to this copper ion over here. But because there's a lone pair right next to this green orbital, which is so the d orbital over here, which is on the axis, it would be harder to keep electrons over there. The electrons in the d subshell will prefer areas between the axes. Okay, so if this NH3 approaches from the top, it's going to be harder to keep electrons in the d orbital, which is on the axis. And so within the d orbital, there's now going to be a difference. There are going to be areas where it's going to be harder to keep electrons. So these shaded green areas, within the d subshell, it would be harder to keep electrons in those places. And it would be easier to keep electrons in the middle part over here. It would be easier to keep electron in these middle orbitals over here. So your d subshell was originally degenerate, which meant that they were all identical. But once a complex gets formed, there would be some orbitals where it would be very hard to keep electrons and they're going to have a higher energy level. And there would be some orbitals where it would be easy to keep electrons and they would have a lower energy. So the d subshell with its degenerate orbitals, they're no longer going to be degenerate. They're going to split into two sets of energy levels. Uh, between the axes, it would be easier to keep electrons, and On the axis, it's going to be harder to keep electrons. ठीक है, यहाँ तक clear? This is what we did last time. Is that clear? Isaac, Ibrahim, Qasim, is this clear?
Yeah.
Okay, and then I told you that electrons, they kind of jump around. If there are electrons in the lower energy d-subshell, they might gain energy and they can jump to the higher energy d-subshell. So it was very vital for colored compounds that the d-subshell has to be incompletely filled. There has to be room over here, otherwise the electrons cannot jump around. If all the d orbitals are full, the electrons cannot move from the lower to the higher one. So, there has to be, the d has to be incompletely. This was one of the definitions of transition metal, that they would form stable ions which had incomplete d subshells, because that would enable the transition to happen. If it was full, they can't move around. I said, now, if they want to gain energy, they gain energy from frequencies that are coming from the visible spectrum. So this energy gap over here exactly matches frequencies that are coming from the visible spectrum. Uh, so electrons go into excited state in almost all atoms. Uh, but the energy gap might be too big, so they would absorb frequencies that are really high, like gamma rays or X rays, or the energy gap between the orbitals might be too less, and they would absorb lower frequencies, like from the radio waves, which we won't be able to see. The only special thing about transition metal complexes is that the energy gap that is created exactly matches frequencies that belong to the visible spectrum. So we wrote down that energy is proportional to frequency. So it exactly matches frequencies that belong to the visible spectrum. So the answer that you're going to write, I'm going to write that answer now. It's going to be a 3-4 mark question. So the first question is, why are transition metal complexes colored? That is exactly what they're going to ask for. And the answer to this is that due to the repulsion from lone pair on ligands, so due to the repulsion that is, this thing, due to the repulsion caused by the lone pairs on ligands, the d subshell splits into two energy levels. So your d subshell splits into two energy levels. And you can talk about the splitting. We're going to talk about the splitting later on. It splits into two energy levels. An electron from the lower energy d orbital can absorb frequencies so it can absorb energy delta E and jump to the higher energy d orbital. So it basically goes into excited state. The next thing that you're going to write is that this delta E, since energy is proportional to frequency, or you can write E is equal to HF, which is basically, H is just a constant. Energy, remember, a higher energy means higher frequency, and a lower energy means lower frequency. So since E is equal to HF, the energy gap delta E exactly matches between the d orbitals between the d orbitals exactly matches frequencies that belong to the visible spectrum. So this delta E is pretty special, the energy gap that is created between the d-subshell. And so it's going to absorb frequencies that belong to the visible spectrum, and hence a complementary color is seen. Which means you're going to see the opposite color. So for example, how do you see light? It's for example, there's a person standing over here, and there's a transition metal complex UH2O6, right? Which is +2. Now white light falls onto it. So white light is falling onto it. White light is a combination of all the frequencies. So it's going to be violet, indigo, blue, green, yellow, orange, and red. And light is going to get reflected and it's going to reach your eyes. Now, in this particular case, I think it's going to, because it appears blue in color, that means blue is the light that it's probably not absorbing. So it would probably absorb the rest of the part, the yellow, orange, and red lights. The blue frequencies are not going to be absorbed. So if it absorbs red frequency or orange frequency, uh, what you're going to see is you're going to see the rest of the frequencies. So a complementary color is seen. So it absorbs red, and that goes missing from the light. And when it reaches your eyes, you're going to see all the other colors which it's not absorbing. Okay, that's why they use the word that a complementary color is going to be seen. Okay, so is this clear? This 4-mark answer about why a transition metal complex is colored. There it. Hala, is this clear, Ibrahim? Isaac, Qasim, is this clear? Clear, नहीं clear?
Yes.
Abad. So I'm just going to repeat everything. The d-subshell, which was actually, I mean, remember, there's no bonding happening. Okay, the d-subshell is within the atom, right? The ammonia, etc., that's on the outside, right? The only thing the ligand is doing is that it's causing repulsion. And which is why, because of the repulsion, it's harder to keep electrons on the axis. And but relatively, it's easier to keep electrons. So the d-subshell splits, and there's an energy gap, and this energy gap exactly matches frequencies that belong to the visible spectrum. Now, the second part of the same question is why changing ligands would change the color of the complex. I mean, if copper is with water, it's blue in color. If copper is with ammonia, it's deep blue in color. So the second question is why ligand exchange changes color of the complex. The answer is pretty simple. That if you change the ligand, so for example, if instead of ammonia I replace it with water, then the lone pairs of water are different, and they're going to create a different amount of repulsion because it's obviously water. Ammonia and water, there's going to be a difference between the lone pairs. The lone pair charge density is going to be different. So if the repulsion is different, the energy gap that is created would be different between the two sets of between the higher energy orbitals and between the lower energy orbitals. So this energy gap would be different, and if the energy gap is different, the frequency of light frequency that's going to be absorbed, that's also going to be different. So the answer is pretty straightforward. That, but it's going to be a long, lengthy answer as well. That what you're going to state is that different ligand lone pairs have different charge density. So they've got different charge density. Uh, Hence, they exert a different repulsion. So they exert a different amount of repulsion. And the energy gap delta E, which is created, between the d orbitals is also different. And the rest is the same. Since E is equal to HF, or energy is proportional to frequency, a different frequency from the visible spectrum is absorbed. So different frequency is going to be absorbed, and hence a different complementary color is seen. So it depends on the marks that the question carries, and your answer is going to be, I mean, mostly it's going to be a three or 4 mark question. ठीक है, ये भी clear है why changing ligands would change the color of the complex. Is that clear? Clear है ये?
Yes, sir.
अच्छा, अब जो next season है, that's I mean, we did the whole complex thing. ठीक है, now the next thing is that so there's going to be another question, which is, I mean, normally they're going to ask you this. They can change the metal line, but so for example, they're going to state why copper +1 complexes are colorless. So that's another question on colored compounds. So why are these complexes colorless? Now, if you look at copper +1, its electronic configuration, if you start off with argon and it's 3D, I mean, it's supposed to be 3D10 4s1, but it has lost an electron, it's got 3D10, right? Now, the d-subshell is completely split, completely full. So what happens in this is that even if it is, if the d-subshell splits because of ligands approaching it, the electrons cannot move between the d-subshells because all of them are full. There's no empty space. They can't jump around. Okay, if they try to go from the lower d orbital to the higher energy d orbital, all of the orbitals are full. So there's no space to jump around. So the answer to that is pretty simple. Why are they colorless? The d subshell is full. And electrons cannot go into excited state, cannot absorb frequencies from the visible spectrum. And they cannot move from lower energy d subshell to higher energy d subshell. Okay, so the d subshell is completely full and electrons cannot jump around. And that's why copper +1 complexes are going to be, इसको highlight कर लेते हैं, they are going to be, they're going to be completely full. So that's why copper plus one complexes are colorless. Now, another important thing is that the splitting pattern, you have to know the splitting pattern as well. So splitting pattern of the d-subshell. Now, there are two types of complexes. I mean, there are many types of complexes, but we just need to study octahedral. Because let's look at octahedral complexes. In octahedral complexes, we just discussed this, that, I mean, this is an octahedral complex, the one that we studied. What happens in an octahedral complex is that all the ligands, they approach on the axis. So it's harder to keep electrons in the d subshell on the axis in these areas over here. So the d subshell splits in a very specific way, and I'm just going to write that down, that it's going to be harder to keep electron on the axis. So it would be really hard or difficult to keep electrons on the axis, and between the axes, it's going to be easier to keep electrons. So यहाँ पे it's going to be easier to keep electrons. Hence, that is how they're going to split. Again, that's so here's your delta E. So now you also have tetrahedral complexes as well. Like if you have ligands that are really big in size, we did discuss tetrahedral complexes early on. इससे पहले था एक second. Yeah, tetrahedral complexes. So not all complexes are octahedral. I mean, there are all sorts of complexes. Remember, you've studied shapes of molecules. Sometimes the ligand is like really big in size, so you can't fit a lot of ligands around it. So it's going to form a tetrahedral complex. Now, if you look at a tetrahedral complex, in a tetrahedral complex, the ligands, they don't approach on the axis. So if you have a d subshell within the copper atom over here, so in a tetrahedral complex, they're not approaching on the axis. They're all approaching between the axis. So the splitting is exactly the opposite in a tetrahedral complex. In a tetrahedral complex, they're actually approaching. I mean, all the ligands, they're approaching kind of between the axis, not on the axis. The angle is 109.5. So it's in a tetrahedral complex, it's going to be harder to keep electron between the axis compared to on the axis. So you got to remember this difference, that the splitting pattern would be exactly the opposite, that it would be harder to keep electrons between the axes, and it would be easier to keep electrons on the axis. ठीक है, is this thing clear? ये clear है कि नहीं clear ये चीज?
Yes.
So it's going to be a different delta E. The whole concept would be kind of the same, except that the orbitals which are at the higher energy level and the orbitals which are at the lower energy level, that's different. Okay, so tetrahedral complex versus octahedral complex. And that pretty much sums up why transition metal complexes are going to be, they are going to be colored. अच्छा, अब the next, so we're done with colored complexes, and they're going to be very typical questions. They'll ask you to sort of fill this up, whether it's an octahedral or a tetrahedral. They'll ask you to draw the orbitals. which one is at a higher energy level, which one is at a lower energy level. Why is copper 1 not colored? Why do changing ligands changes color? Ask you to, I mean, about the complementary colors. They might ask you to predict what the color of a complex is based on what frequency it's absorbing. Sorry, colors over. So based on the frequency that it's going to absorb, basically I would need to know what the visible spectrum, right? What are the frequencies? I think it's 300 to 700 nanometers. Just one second. Visible frequency range. 400 to 700 nanometers. I mean, that's the wavelength. So you've got 400 nanometers wavelength and around 700 nanometer wavelength. So all I need to know is what is that 400? Is that the 400 we're considering? Is it red or blue? One second. Just hold on a second. 700 is 700 is red, and 400 is, I'm going to call it violet, and we can divide all the colors. Okay, so I guess this is how. If you space with your equally, so you need to have some idea about which frequencies are getting absorbed and which ones are not getting absorbed. Okay, so they might tell you about the absorbance. A colorimeter would show you the absorbance that's happening. I said now about the complementary color. Let me just Google a chart on complementary colors. Okay, instead of Googling it, I'll make a circle. So I need to, it's violet, indigo, blue, green, yellow, orange, and red. Okay, I just need to space them properly. So I guess ये थोड़े करीब हो गया. So I guess this is how it's going to look like. Now about complementary colors. The way things are going to appear to you. So if some complex is absorbing violet light or violet frequency, for example, this is absorbed, you're going to see all the other colors, but you're not going to see violet because it's going to absorb the violet frequency. So when light gets reflected, it won't have violet color. I said, so how do you figure out what the rest of the colors are? I mean, you're going to see all the other colors, but without the violet. Now, the combination of all the other colors, that will be, if you think of it as the circle, the complementary color would be all the other colors combined. It's going to be the opposite side of the circle. Okay, so what you're going to see is something that's going to be greenish yellow. Okay, is this idea clear that if all the colors and the complex absorbs, it absorbs violet, then think of it as the circle. The mixture of all the rest of the colors go at the opposite end of the circle. So all the other colors, if you mix them together, you're going to see something that's greenish yellow. Okay, is this clear?
Yes, sir.
Or similarly, if something is absorbing this frequency over here between orange and red, or reddish orange, right? So what you're going to see is go all the way across the circle. You're going to see blue. Okay, and so on. So this is how you figure out what the complementary color is going to be. Okay, so you're going to see all the other frequencies that the complex is not absorbing. Okay. So you need to have some idea about, and you also need to know uh, on the wavelength scale which one is violet, which one is what are the rest of the frequencies. So if they make a graph which kind of looks like this, and they tell you that these are the frequencies that it's absorbing. So you would notice that the maximum frequency that it's absorbing is the blue one. So that means if it's absorbing blue, what are you going to get? You're going to get something that's reddish orange. Okay. So across the circle, that's what you're going to see. So okay, that's all about colored complexes. Uh, and it's going to be very typical questions on colored complexes. We'll do past paper questions, so you'll see. ठीक है ये सारा clear है सारों को but is this clear हाला Ishaq Ibrahim clear है all of this
Yes, sir.
अच्छा अब the next thing is where's the syllabus अच्छा so अच्छा next is I mean there's very little left now अच्छा the next thing is you need to understand what a monodentate ligand is. I mean all the ligands that we did they're all monodentate. So it's a species which can form only one dative bond. That's in a metal complex. So all the examples that we did so far, what is a monodentate ligand? Ammonia is a monodentate ligand. It's only capable of forming just one dative bond. Then you have bidentate ligands. Now, bidentate ligands, again, if they ask you for the definition, it's a species that forms two dative bonds. Dative covalent coordinate bonds in a metal complex. And there are two specific examples that are mentioned. One of them is the ethane dioate ion, which is this one. And the other one is ethane 1,2-diamine, which is CH2, and then you've got NH2. So it's like two ammonias joined together. I said so this is ethane 1,2-dioic acid, and this one is ethane 1,2-diamine. I said these are bidentate ligands. So time come, I'm just going to draw one. What does a bidentate ligand looks like? So for example, I've got the same copper ion, and as a six things will try and datively bond or get attached to it. Okay, so imagine these are your X, Y, and Z axis. So okay. I said now let's think of ethane 1,2-diamine. So think of it as two ammonias. So you've got an ammonia, like NH2, and you have another NH2, except that they are joined together by a carbon chain. So one N forms a dative bond from one side, and the other N forms a dative bond from the other end. The same thing would happen over here as well. And in the middle, you're going to have and then you're going to have one more, which is NH2, and so N forms a lone dative bond from this side, and there's an N forming a dative bond from the other side. ठीक है? Is this clear? ये clear है? What a dative bond, what a bidated ligand is.
Yes.
ठीक है? And the whole thing is going to have, because ethane 1,2 diamine was neutral, and the copper that was in the middle. एक second. I said the copper that was in the middle had a +2 charge. So overall, it's going to have a +2 charge. Okay? And the way you're going to write this is it's copper and NH2, CH2, CH2, and NH2. And there are three of them. You can put them together. There's copper +2, and this is neutral ligands getting attached to it. Put square brackets, and it's going to have overall +2 charge. Because that's what a bidated ligand is. They can give you any bidated ligand, you just have to draw it. Okay? It's not going to be rocket science. It's just going to be a very simple question. Okay? चलो ठीक है. There's very little left, so we'll try and cover that, and I'll share the notes tonight. ठीक है ये सारे. चलो ठीक है. Okay, everyone.
Okay, sir. Allah Hafiz. Thank you.
Hafiz.